All right. All right, here we go. So, um, as Sarah, I think mentioned, this is a kind of a two-parter that Jim and I wrote a few years ago, and Sarah was interested in us talking about it. So I thought I would give you a bit of a quick and slapdash overview. Maybe I'll start with a little bit of a motivation for how we got into this project, and talk about a few conditions that we think people often discuss as expressing what it means for special relativity to be locally valid in general relativity, but that we think are either wrong or missing something or not sufficiently perspicuous. And this led us to do a little bit more of a geometric reformulation of some of these ideas that we think is perspicuous about the way in which special relativity is locally valid, that also throws light on what kind of interpretive significance this may have. I think that it's important then in the motivation to talk about uh, how we got into this. So people invoke the idea of space-time being locally flat or locally Minkowskian or special relativity being locally valid. I'm going to use all of these interchangeably uh, to sometimes, describe a heuristic for how they develop a relativistic theory of gravity. Sometimes it's supposed to be merely a deductive consequence of general relativity that's useful for approximations. So you deduce after postulating general relativity that there are certain features that hold locally, and you use these to, for instance, pragmatically simplify calculations or allow you to interpret things relative to a simplified or idealized spacetime. But some people also take it as a principle, right, that enables the interpretation of general relativity. And this sort of tradition is quite old. It's one that we find in Einstein, even. And this is the one I think that Jim and I were most concerned about whether it was viable given how we ultimately cash out what it means for space-time to be locally Minkowskian in some sense. So, for instance, here's a translation of a passage from a letter from Albert Einstein to Paul Painlevé in 1921, expressing this sort of idea. Einstein's not the only one who expresses this sort of idea. Many others do, but I think this is very this particular passage that Dennis Lemko translated a couple of years ago from a letter from Einstein to Paul Painlevé in 1921 expresses the kind of attitude about the relationship between special relativity and general relativity that gives it substantive interpretive significance. Einstein says that GR rests entirely on the premise that each infinitesimal line element of the space-time manifold behaves like that of special relativity. Um, and this permits the infinitesimal coordinate systems and inertial systems, with the help of which the space-time interval, the ds, are to be defined exactly like in the special theory of relativity. And he says that the GR stands or falls with this interpretation of the space-time interval. Stands or falls, right? So it depends on the latter just as much, he says, as Gauss's infinitesimal geometry of a surface depends on the premise that an infinitesimal surface element behaves metrically like a flat surface element. Now, there's a lot of interpretive questions about what Einstein means exactly here, but we see those interpretive questions rising again and again in subsequent literature. So instead of focusing so much on the Einstein exegesis, we're going to try to look at a few different interpretations to clear the ground for what we think is the most perspicuous way of understanding the relationship between the two in terms of geometry. So as I said, I'll be focusing on the geometry aspect because there's a separate question if you're thinking not just about the relationship between the spacetimes, but the relationships between the theories as stages for material dynamics, then there's a separate question about how matter fields behave in special relativity compared with how matter fields behave in general relativity, which Jim will talk about next week. Okay, so one of the things I wanted to mention, because, we've already had some discussions with people about these papers, and I think people maybe have reacted in ways that have surprised me and Jim, um, is to clarify what we think the question that we're asking is not. So we're not merely asking, does Minkowski spacetime uniquely have some local property among relativistic spacetimes? You can come up with lots of these properties that Minkowski spacetime has, um, uh, but uh, the property that, in order for that to be relevant for the questions we're asking, these properties need to just not to exist, but they need to have some heuristic significance or practical significance or interpretational significance. And we think oftentimes there's a case for them to have heuristic or pragmatic significance, but the case for them having interpretational significance, we think, is less substantive. So that's kind of what ultimately was, at least for me, driving the target of the paper, is these sorts of passages like the ones you saw from Einstein that seem to indicate that somehow we need to have or postulate a special relationship that general relativistic spacetimes can have in order for it to be interpretable. Um, and we wanted to know what kinds of like technical features of spacetime could underlie such claims. So let's briefly go through a few that we think are don't work or that are not perspicuous in some sort of way. Okay, so here's a literal interpretation. Every relativistic spacetime is locally isometric to a flat spacetime. So that's a literal reading of the statement that relativistic spacetimes are locally flat. But we know that it can't be correct. Just as a reminder, a space-time's flat just when its Riemann tensor vanishes everywhere. And we say that a space-time is locally isometric to another space-time when for every point in the first, there's a neighborhood of that point and a smooth map that maps into the second space-time, such that the space-time metrics match at each point. So for instance, uh, yes, here we go. You can imagine, diagrammatically something like the following. We've got a space-time here. Here's our point P. Here's our neighborhood, U, P, and then we have some other space-time over here. So this is M, this is M prime, and we have a map that goes from here into here, such that the space-time metric, which I might draw a cartoon of using this little triangle here, when we push it forward along or when we pull back the metric here, they match up exactly at every point in this neighborhood. So the idea is there's a little portion of M here, which, as far as everything is concerned regarding the mathematics relativistic spacetimes, is the same kind of structure as a little region of M prime over here. Okay. So given that, we know that local isometries preserve curvature. This is just a technical feature of isometries. And so we know that the literal interpretation can't be true because any spacetime that has any curvature at all can't be locally isometric to a flat spacetime. Now, uh, oftentimes this is a kind of interpretation that people say casually in some sort of shared context where probably people don't fall into this sort of mistake. But it's close to another kind of interpretation that we saw quite early on in relativity theory. So this is a version of a kind of this sort of idea that we see in even in Pauli's encyclopedia entry on relativity theory from 1921. We'll call this the coordinate chart interpretation. So according to this one, in a sufficiently small region of a relativistic spacetime, coordinates may be chosen relative to which the Christoffel symbols of the Levi-Civita connection vanish. That's the one compatible with the metric. So the issue with this is similar to the issue with the first one. Christoffel symbols vanish on an open region if and only if the region is flat. And so the coordinate chart interpretation is false for the same reasons that the local flatness one is. We're going to come back to another version of this coordinate chart interpretation in a second, but let's go to a third option first. We'll call this the tangent space interpretation. So oftentimes you see statements like this: the tangent space at a point of spacetime is or is equivalent to Minkowski spacetime. So in this cartoon that you see here, we've got a spacetime manifold M, a point of the manifold X, and a representation, a kind of cartoon of the tangent space TXM here. So the idea is supposed to be that the tangent space is a kind of Minkowski spacetime, or it's equivalent to it in some relevant way. So this has some things going for it. So it is true that the tangent space is a smooth manifold, and the metric at a particular point. So if we had a space-time metric, for instance, um, at this point x, uh, if my uh, if I can get my things to work, here we go. You know, if we had a space-time metric at a point here, this using some standard apparatus could be mapped to and generate light cones on all points of this surface here simply by parallel transport. So there's a way in which the space-time metric at a point determines a Lorentzian metric on the tangent space as understood as a manifold. However, the tangent space has the structure of a vector space. It has a privileged point, a 0 point. And of course, general spacetimes don't have that. That extra structure is not just a technical difference, but it makes an interpretational difference too, because its points, the points of the tangent space, represent instantaneous directions in spacetime rather than events. And so the sense in which it has the same structure as Minkowski spacetime doesn't mean that it admits of the same interpretation, doesn't represent the same sorts of things. For instance, this means that the lack of curvature of the tangent space doesn't reflect anything about spatiotemporal curvature relations at the point x or in the neighborhood of x. And this just derives from the fact that the points of the tangent space don't represent events at all. They represent directions or magnitudes and directions.
Uh, Let me ask a question. So, does the tangent space have any physical interpretation at all?
Yeah. So the elements of the tangent space represent instantaneous directions and magnitudes of directions at a space-time event. So, for instance, um, oftentimes in the context representing representing curves like we do here, the tangent vector of the curve, which here is represented by v, um, represents, as it were, the instantaneous direction of travel of the history of the particle whose world line is given by gamma. And there's similar kinds of interpretations or analogous or related interpretations you can give to other sorts of curves. So the points of the tangent space do have an interpretation, but they represent something different than the points of the manifold do. Does that answer your question?
Yeah, I think so. And I guess for you, the fact that those kind of trajectories have a kind of Minkowski structure, or locally the directions in which the trajectories work are Minkowski, that isn't enough for your interpretational demand. Is that right?
Yeah, it's not enough that they share some mathematical structure. It's got to be that in addition to sharing mathematical structure, that those mathematical structures are representing either the same or sufficiently similar things so that you can understand one to be, for instance, approximating the other or being a stand-in for the other. And that can only be the case if they're playing the same roles, but they play the same one way they play the same rules is by representing the same or very similar things. And they're not doing that here. I think that formally
Sorry.
speaking, the fact that the tangent space, right, is a vector space is representative of this sort of feature, right? So because the fact that we're representing directions means that we have a privileged element, the null element, which represents no direction at all.
Okay. We have another question, Ramesh.
Yeah, so I think it's more than directions. Maybe I've got this all wrong, but when you read relativity texts, and I'm thinking of Hartle's beautiful book, they always say, go to the local orthonormal frame, right, with orthonormal coordinates. That's the frame in which you can easily calculate observables. What is the magnitude of this? Or, what is the dot product of those, et cetera, et cetera. And I always interpreted it as you're sitting in a local tangent space, Minkowski structure, and that's where you're calculating stuff, even though the overall space-time may be, curved and all that. Are you saying that I have the wrong picture, that that's not what we are doing with orthonormal coordinates?
We're doing something slightly different, and this is going to be related actually to option 4. So a very, very excellent cue for the transition. Thank you.
Okay.
Yeah. So what allows us to connect the structure of the tangent space to a neighborhood in space-time is the exponential map. So here's another cartoon of the exponential map here, and I've lifted in the image, or actually Barrett O'Neill has lifted in the image that I took from him, the tangent space away so you can see a little bit better what the correspondence is. So the exponential map allows us to take elements in the tangent space and at least locally, so in a neighborhood of the zero element, map them to elements in the neighborhood of the space-time. So I think that what you were describing is a situation where this frame induces a particular choice of basis in the tangent space, and then this induces a little coordinate chart in a neighborhood of the original point. And we can move between the little chart and the tangent space for certain purposes using the exponential map in its inverse, because for a sufficiently small neighborhood, the exponential map is in fact a diffeomorphism. And so we can move back and forth between them. Of course, for a sufficiently large neighborhood, it no longer becomes one-to-one necessarily. So it always has to be a sufficiently small neighborhood. So this sort of version, I think Jim and I like a bit better. And here's a particular statement of it that uses this sort of connection. And it's formulated explicitly in terms of the coordinate chart that you get in the local neighborhood of the manifold. So here's a revised kind of coordinate chart interpretation. At any point of a relativistic spacetime, local coordinates can be chosen such that at that point, the components of the metric agree with the Minkowski metric and standard coordinates, and all the Christoffel symbols vanish. Now, the difference between this version and the previous version that we saw before is that we're not demanding that the components of the metric or the Christoffel symbols vanish on the whole neighborhood. We're only demanding that they vanish at a single point, or maybe in certain generalized versions of this, along a segment of a curve. The significance of this is that you do allow for the Christoffel symbols to be non-vanishing outside of the point, but simply through a standard continuity argument, you know that whatever coordinate system you want to use to represent them, they'll always, in a sufficiently small neighborhood, be of sufficiently small in magnitude. So we think that this is a better representation of the idea of what it means for special relativity to be locally valid, but we do think that it's not perspicuous in certain ways. So one thing that I think that we would want to answer is, what does the form of the metric in some coordinate system really inform us? Right? Because the statement right now, as it states, is it's telling us something about the representation of certain geometric objects using certain coordinate representations. But what is ultimately the significance of that interpretationally? It pragmatically, it may have an obvious benefit because it simplifies certain kinds of calculations, but does it have any interpretational benefit? Now, the fact that, going back one slide just a second, that the claim here is an existence claim. There exist local coordinates that have these features, of course, is compatible with the fact that there's coordinate systems that don't have these features. So, what do we make of the difference between the existence of local coordinates that satisfy these features and ones that don't? Why do we find the ones that satisfy these more important than the ones that don't? And which features of the coordinate systems have to be salient? One of the things that is going to be relevant here is that statements like these, because they're stated as existence claims, it can be tempting to read them as a kind of uniqueness claim, that there's a unique such coordinate system, or at least a highly constrained equivalence class that have this feature. But in fact, that's not in general going to be true, as we're going to see later on. There's going to be lots of different coordinate systems like these that don't agree with one another regarding what the relevant straight coordinate lines are. Okay, so this motivates an idea about giving a geometric formulation to these sorts of ideas. One that abstracts away from particular representational features, which are important pragmatically, but that try to see if we can find any interpretational significance to these sorts of claims. So just a little bit of terminology, because the claim that we'll use invokes the notion of an embedded curve. So just remember, an embedded curve is one whose image is an embedded submanifold. So here's statements of it. We've got a space-time and we've got an embedded curve and we've got a point on the curve. So if you wanted to see it visually, it would be something like this. We've got a manifold, green manifold this time. And we've got our curve gamma, and we've picked a point on the image of the curve. So here's P. This says that on some neighborhood containing P. So here I'm going to draw a neighborhood O. We can find, or there exists mathematically, a flat metric, G bar, that agrees with G on the region of the curve that's inside O. So that's this region in here. And moreover, the Levi-Civita connection also agrees on this region here, just this green part within the curve. And through continuity reasons, we know that outside of that, they have to they don't agree, but they diverge from one another in a continuous way.
But you mean the red part, right? Agree within the red part.
Maybe I'll highlight part where they agree is along here.
I see. Okay.
Yeah. So there's ways of giving even more general and abstract features of this result. So we can replace gamma, in fact, with any embedded submanifold that has vanishing intrinsic curvature. It just so happens that points and lines always have vanishing intrinsic curvature. So you can always do this with a point, and you can always do it with a line, provided that, and this is guaranteed by the fact that the curve is embedded. So it's not self-intersecting.
So what is the neighborhood doing here? The whole.
Yeah. So what the neighborhood is doing is it's providing a region that circumscribes the. I should go back and draw. It's circumscribing the regions that determine this point here and this point here. So what's significant about the neighborhood here, O, is not, as it were, its fatness in the diagram, but where it's going to be intersecting the curve. The idea here is that the points where you can do it, but maybe I'm understanding your question.
Well, and my question is like, you're not talking about some sort of segment of a curve. So you've sort of selected a neighborhood, but most of the neighborhood seems to be not featuring in your statement. Or maybe it is and I'm missing it.
No, you're right. Most of the neighborhood doesn't feature in the statement. This particular way of describing it is, I guess, mathematically convenient. But if you wanted to, you could do something like pick two further points on the curve that bound P and construct a tubular neighborhood around that.
Okay, Ramesh,
Yeah, I'm trying to get an intuitive grasp of this theorem one. So if I imagine that my curve gamma is a corkscrew, to me, that's kind of, the basic element that's very hard to fit within a plane or a flat metric. So if I start with a helical gamma, how do I even visualize that this theorem is true? Is it that if I choose a small enough neighborhood, it would still be consistent with a flat metric? Is that the trick?
So just to make sure that I understand, you're imagining a situation like the following, where you've got a curlicue like this. Is this what you have in mind?
Yeah, yeah. There is some kind of extra torsion in my gamma.
I see. Yeah. So what's really important here is that as long as this curve is embedded, then that means that um, if you look at some arbitrarily small neighborhood around it, it's still a non-intersecting curve, and the points of the curve don't get arbitrarily close to one another. And so even though I've drawn this neighborhood O as being very fat, in principle, it could be very skinny. And the fact that the curve is embedded will allow us to draw a skinny tubular neighborhood around any region. Does that help answer the question?
I think so, yeah. Thank you.
Okay.
there's another question. So Daniel, do you want to?
Yeah, thank you. So I wanted to know if this would work for any arbitrarily big neighborhood, because how local could that be if this could get arbitrarily large?
So in general, that's a good question. How big can the neighborhood be? I think that how big the neighborhood can be will depend on the details of the space-time. The way that we maybe if Jim remembers better than I do, he can interrupt. But my recollection is that the way that we prove this in such a general way makes it so that we don't have quantitative bounds on the sizes of these because we wanted to prove a general sort of result of the kind that we often find in invocations of the general local validity of special relativity. But like with a lot of these sorts of general results, if you want to give quantitative bounds, you need to have some quantitative information about the space-time. And because this result is general, right, we can't provide those quantitative bounds. But I imagine that if you're able to describe the space-time in some more detail, then you would be able to describe the size of the neighborhoods of particular sorts of curves in more quantitative detail. So I'm sorry that I can't give a more specific answer, but I think it has to do with the way that we've set up the problem in that sort of way.
No, that's the answer I was looking for. Thank you.
Okay, cool. Good. Um, so we think that this theorem allows us to express a sense in which Minkowski geometry approximates arbitrary local Lorentzian geometry. So the way that it's doing that, right, is that it's getting exact matching along the portion of the curve and approximation in a neighborhood thereof. We can make this a little bit more precise. I'm not sure how much technical details you all want to go into. There's a lot more about this in the paper. The main idea, though, is that you have a norm on tensors that you induce by a frame. Basically, you express a tensor as, for instance, in particular components according to a frame, and then you can uh, do things like add up the sum of squares of the components, and that generates a norm. The details of how the norm are generated are not really that important as long as it has generally nice features. The thing that we want is to have a distance function between two tensor fields of the same rank. So if f and f prime are two tensor fields, you can look at the magnitude according to the norm of their difference over some region and take the supremum of that. And you can also, in addition to the values of the tensor fields, also look at their derivatives. And so you can define a distance function that measures how far apart two different fields are, not just by their values, but up to a certain number of derivatives, so k derivatives in this particular case. So what's important about that is that it allows us to define a notion of approximate isometry. So if we have a diffeomorphism between two regions of two regions of two different spacetimes, we can say that they are hk epsilon isometric just when the distance between, on the one hand, the spacetime metric on the one region is less than epsilon away from the pullback of the metric on the other region. So if you wanted to have a picture for how this works, it's a picture that looks a little bit like this. Here's our region U. Here is, I'm going to try to write it. It's supposed to be the similar shape, but you'll be patient with me with the fact that the shapes are not exactly the same. You know, we've got metrics like this, and we have a map that will map between them. And we can pull back the metric along here. And we compare, for instance, this red triangle pulled back with this red triangle and all of the other metrical structure as well, using this sort of technical machinery. And we figure out what the maximum difference is, and that gives us a distance between them. So if the distance between them after matching between them is less than epsilon, we can say that, they're almost isometric. And all of this machinery here in front of the isometry is just to label the sense in which they're approximately isometric. We've got an epsilon, we've got an order of the number of derivatives that we care about, and we have the particular norm that we're using to determine that.
So Sam, is this so often when often people display approximate isometries, they start out with the metric written in some form, and then they sort of do a Taylor expansion or some kind of other perturbative expansion, and then they show that, well, look to the first order or first couple of orders, they're the same as some other metric. Is this machinery essentially just making that more precise?
It's related to that. In a Taylor expansion, typically you have some parameterized family, and the Taylor expansion parameter is related to that. So in that particular case, you want to have, for instance, a space-time or structures in the space-time that are expressed by some complicated function. You take the Taylor expansion and you truncate it because the parameter you think could play the role of the kind of something related to this sort of epsilon. So I think it is related to that. And indeed you can formulate, I think, a lot of these constructions in the terms given here. The substantive difference here is this is quite general, so it doesn't necessarily need to be the case, for instance, that you have any particular Taylor expansion in mind. You don't need to have any particular representation of the geometrical structure in terms of coordinates. If you wanted to do concrete calculations, of course, that is what you'd need to have. But like I said in response to a previous question, part of our goal to have the analysis here at a certain level of abstraction is so that we can try to abstract away from details that don't really matter to the biggest conceptual point.
Okay.
Cool. So this allows us to prove a kind of corollary. So this is a kind of an informal version. So what this allows us to say is that this neighborhood that we were talking about before, you can always construct it in such a way that there is an approximate isometry between it and a neighborhood in Minkowski spacetime. That has the feature that there's a curve in Minkowski spacetime that matches up with the curve in the original spacetime. So pictorially, the sort of thing that I have in mind is we have once again our spacetime M. Here is our Minkowski spacetime. Here is our curve. Here is our neighborhood O. And now we've got a map that allows us to go from here into here. So that if we do chi after gamma prime, it gets us to gamma in this region O here. And moreover, this region O here is approximately isometric to a relevant neighborhood that you can generate by pulling back O along chi into Minkowski spacetime. So this gives us a way of formulating this approximation conditions on O. So if you had a tighter epsilon, for instance, that you wanted to give, the width or fatness of O would have to be correspondingly smaller. But like I was mentioning before, because we're doing things at a certain level of generality, we don't have particular quantitative bounds on those. But you could get those sorts of bounds if you had working with a more specific space-time. Was there a question?
No, I think things are good.
Now,
No.
the thing that's interesting about this is that there's many different normal coordinates that are adapted to the metric and that correspond to different choices of standard Minkowski coordinates. So what that means is that the particular map that I drew that's mapping into a particular region of Minkowski spacetime is not unique. There's going to be many such maps. Indeed, in general, there'll be infinitely many. So the sense in which a spacetime is approximated, say by a Minkowski spacetime in a region, is not unique. There are many different ways in which Minkowski spacetime can approximate it. This is a little confusing if you don't think about it with sufficient care, because of course there's only up to isometry only one Minkowski spacetime. So how can there be many different ones? It has to do with how, for instance, you orient or of course or map together the light cones off of the curve. Maybe I can draw this a little bit for you. So this is in our space-time. Here's a Minkowski space-time. And here's another version of Minkowski space-time. They all may map together on the curve, but outside the curve, it could be that these map to cones that diverge off in this sort of direction. But these, for instance, map off to cones that diverge off in the opposite direction. Imagine this tilting in a smooth way. And it might be possible to map the spacetimes in this sort of way that match nevertheless on the curve. So these are two different ways Minkowski spacetime could approximate a region around a curve. Okay. Good. So let's call a spacetime fulfilling the role of Minkowski spacetime in this corollary a universal locally approximating spacetime. these universal locally approximating spacetimes, you can always use them to locally approximate any spacetime in some small region. We're going to use this terminology later on when we come back to another way in which Minkowski spacetime is not unique in this respect. So another result that we have is that for any sufficiently small neighborhood of a point on the image of an embedded curve, there's many of these flat, universally locally approximating spacetimes. This is just maybe a restatement of the kind of picture that I gave before. Since we're running a little bit late, I'm going to go next to the next result here, which is what I alluded to just a second ago. So according to this result, in fact, every space-time is a universally locally approximating space-time, not just Minkowski space-time. And the proof for this is actually very simple. It just comes from the fact that if you have a space-time A, which approximates a space-time B, and a space-time C, which also approximates a space-time B, then because the notion of approximation takes place within a metric space, we can do some composition of epsilons so that if each of them are approximating within some epsilon, the A and C will approximate each other within some function of epsilon. So if you pick that function of epsilon to be sufficiently small, you can always find approximations that, as it were, epsilon transitive with one another. So the idea, in other words, is if you have Minkowski here, and two spacetimes here, and you have an approximation that happens on a region of each of these, you can have these two regions overlap, and then in this overlap region, you can have the approximations compose with one another, so that you have a region here, which is approximating a region here by going through Minkowski spacetime. At least that's how you prove it. So the important significance of this is that even though in terms of geometry, every spacetime is locally Minkowskian, every spacetime is in fact locally every other spacetime. What that means is that Minkowski spacetime doesn't have a special role here, except insofar as it's more calculationally easier to calculate things in Minkowski spacetime than it is in many other spacetimes. So if there is a special interpretive significance to Minkowski spacetime that comes through this sort of idea, it can't come through a unique feature that Minkowski spacetime has that these don't have in this particular respect. Now, sometimes people talk about the local validity of special relativity as implying or involving the symmetries of Minkowski spacetime. So we can address this question in the help of our theorems 1 and 5, provided we have a couple of more definitions. So let's say a smooth vector field on a relativistic spacetime generates an approximate local symmetry near a point, just in case when we Lie derive the metric with respect to that vector field, at that point we get 0. Now, of course, the fact that this occurs at 0 means through continuity reasons alone that in a neighborhood of P that that this quantity relative to any norm that you would pick on the space-time metric or on tensor fields in general will be sufficiently small. So the idea is that if this condition is satisfied, then it's satisfied, as it were, within epsilon in a neighborhood of it. And we can say that a spacetime admits local approximate Poincare symmetries at that point, just in case if it has a neighborhood where there's 10 approximate local symmetries, whose generating vector fields satisfy the commutation relations of the Poincare algebra. So we're identifying, as it were, what kind of symmetries they are by what kind of commutation relations they satisfy. So once we have that, we can show that every spacetime admits of local approximate Poincare symmetries. I think this is not particularly surprising, but it's a pretty straightforward uh, step from here to the fact that every spacetime admits local approximate symmetries of any spacetime. And this just has to do with the fact that the condition that we gave before for local approximate symmetries is very easy to satisfy. Now, what this means is that when it comes to pragmatics, oftentimes having lots of symmetries is very, very helpful. The more symmetries that we have, the more easy it is to calculate various things, the more the things that we're interested in are well defined. So it makes sense why we're particularly interested for pragmatic reasons in local approximate Poincare symmetries. But it doesn't mean necessarily that it has any particular foundational significance over practical significance. And we think that this second proposition here makes that clear. Okay, so I hope that that's very, very brief and quick review of some of the things that we did in our paper will help motivate the further question of if Minkowski spacetime is not so special, is there anything that's special about special relativistic matter dynamics? Maybe that's the thing that is interpretationally significant, and that's a question that Jim is going to address in his talk next week. Thanks for your patient attention, everyone, and sorry about all the computer glitches.
No, not your fault, Sam. Sorry about it. Sorry, Charlie. I think the connection is stabilized for now, so we have a few minutes for discussion. Yeah,
Yeah, so thank you for this interesting talk. You phrased everything in terms of space-time, Lorentzian metric, pseudo-Riemannian space-times, etc.
Right.
But does it all apply equally to just ordinary Riemannian geometry? Is the fact that this has got a time axis important at all, or can we just state all these theorems, in terms of what is a curved space and how does it map to a local Euclidean patch or whatever? Would it all just translate, or is there something more here?
Yeah, that's a great question. I think that much of it does, but there's a few things that might be particular to Lorentzian geometry. So if, for instance, if we're interested in particular in Poincare symmetries, of course, these are only going to be symmetries that that only spacetimes with Lorentzian metric signatures have. So if we were considering a geometry that had a Riemannian signature, for instance, we wouldn't get this sort of feature unless I'm mistaken. Um, I could be actually. Let me think about that. I think I will pause and think more about your question actually, because there is a sense in which I think that a lot of these ideas really just depend on general features about smooth geometry. I need to be a bit more careful before I make generalized statements about where it applies and where it doesn't apply. I think that, in a certain sense, it's kind of grist for our mill, though, because we do think that if there is that the features that people often point to as having interpretational significance are very generic features of geometrical spaces and geometrical models. But I will have a more of a thought about whether there's anything that's particular to Lorentzian geometry over Riemannian. So thank you for that question.
So unless there's any questions coming from Zoom so far, let me ask. So, is there a sense in which so grant that every spacetime can be used to locally approximate any other spacetime, but is there a sense in which Minkowski is somehow the simplest one? So it's obviously sort of the best one to use for pretty much not any purpose, but for most purposes.
I think that it often is, and I think that how should I say? This is why I had this slide earlier on where I would try to distinguish different ways in which a special feature of Minkowski spacetime would be relevant for the kind of questions that we want to ask. And the questions that we want to ask, I think, concern the heuristic, pragmatic, and interpretational significance of Minkowski spacetime vis-a-vis other models of spacetime. So I have no objection to the idea that Minkowski spacetime, because of its high degree of symmetry, is often the preferred uh, idealization would give to perform all sorts of calculations. In fact, I think that that's just generally true, that it is. Um, but that doesn't necessarily imply by itself that Minkowski spacetime therefore has any special interpretive significance for GR, except any significance that it might have vis-a-vis that pragmatic significance. Does that make sense?
Let me ask the question another way. So if you look historically, right, like we first discovered Minkowski structure because that was kind of explaining puzzles about speed of light, simultaneity, and all of that, and then generalized to GR. But if I take your story seriously, that's just an entire accident. Could have been that, we first started out with, I don't know, Schwarzschild or whatever, and then stitch that into a global story. But that seems like a rather strange historical trajectory. I'm not saying it's impossible, but it just seems interpretationally, it seems very difficult to imagine in some way.
Yeah, I guess maybe I'm a bit a bit more open-minded. So maybe so I mean, I think part of the reason why it seems so strange is that the problems that Einstein was occupied with weren't exactly, the problems that are often attributed to him, right? He wasn't trying to explain the Michelson-Morley experiments or anything like that. He was puzzled with an asymmetry in explanation in standard electromagnetism and wanted to come up with a way in order to bring two kinds of explanations for this, like electric and magnetic inductive effects, to be on a par with one another, so they're kind of unified. Because the explanations depended on features of the phenomena that were not empirically accessible, about what thing was truly moving with respect to the ether and which thing was at rest with respect to the ether. So, his motivations were quite different, and it led to these. And one of the things that's amazing about the theory is that it led to these enormous consequences for other parts of physics. That's everything that you hope for when you do theoretical physics. You're motivated by an idea that has consequences for lots of things you had no idea it would have. Um, Part of the reason why I'm a bit more open-minded about how the order of development could have gone, at least in principle, is that we see other kinds of. I'll put it this way. So after the development of relativity theory and the development in particular of the conception of space-time as the venue for dynamical theories and for gravitational theories, it gave us the opportunity to reformulate non-relativistic theories using new mathematical tools that weren't available, and really clarified and cleaned up our conceptual picture of what was happening in Galilean space-time, Newtonian gravitation, in a way that wouldn't have been possible if these seemingly more complicated developments hadn't taken place. So if the kind of objection is like, is it really so plausible that the complicated thing could have taken place before? Well, in this particular case, the complicated relativistic thing took place before the new tools that we had available to see the seemingly simple um, platform or theater or stage of Newtonian space-time in a new light that really clarified its structure. So I think that maybe there's a kind of story that you could tell that has that kind of structure to it. Of course, the heuristics that are helpful are really highly dependent upon the research context that someone is working in. So that's why I think this story about Einstein here is very revelatory.
Okay, so we are at time, but since we started late, Jacob, can you quickly ask your question so that
Yes.
we can, like a few minutes?
I can ask very quickly. So I'm surprised you didn't mention the equivalence principle in this talk. You know, when I teach
Yeah,
general
it's in the
relativity,
paper. Yeah.
yeah, when I start general relativity, right, like the first thing, you know, when we begin with a review of special relativity, and then we say Einstein's key insight, right, that his happiest thought was the equivalence principle, the idea that if you give me any point in space-time and I'm in free fall, what we call these locally inertial or free fall coordinate systems, a free-falling observer who constructs in 3D a Cartesian orthogonal coordinate system will, in an infinitesimal neighborhood of any given point, experience what feels like special relativity. Now, this comes with some statements about what's going on with material, and I know that Jim is going to talk about that next time. But I just don't understand how we can make any statements about the preferred status of flat metrics in the absence of talking about all the details that go into the equivalence principle. So I guess my question is, should I just wait until next week for us to talk about that, or is there something you'd like to say about that here?
I think you should come back next week.
Okay, yeah. Thank you.
You're welcome.
Okay, on that note, thanks, Sam, and Jim, we'll see you next week.
Right. Thanks again, everyone, for your patience.
Bye, everyone. See you next week.